Okay, well, welcome everyone for today's fourth lecture of our PWF Quantum Machine Learning course. I'm glad to see everyone here, and for everyone that's watching on Facebook, I hope on Facebook and YouTube, I hope you all are having a great day, and thanks for tuning in, and thanks for all the awesome questions that have been coming on from the YouTube chat. So today, I want to briefly tell you about what we're going to be doing. I know that yesterday I promised that we're going to be looking at the ansatz design problem and maybe some of the difficulties of designing ansatz like barren plateaus. We will discuss the ansatz design problem, but I will probably discuss barren plateaus tomorrow because it's a quantum machine learning course. Thus far, we've been talking about variational quantum algorithms. So I would much rather start today discussing about quantum machine learning, what it is, what can we do with it, and how can we use the basic framework and the basic tools that we have developed for quantum machine learning implementations. So as usual, let's briefly recap what we did last class because there's some stuff that we're going to be using. So it's always good to take a step backwards. So last time what we said, we were trying to analyze the cost function and the different parts of the cost function that we're currently analyzing, which are just expectation values of some operator over a state that has evolved through a quantum circuit. And one big question that we had is what sort of operators are we going to be considering? What this Hermitian operator here that determines the problem at hand? We said that we were going to consider two cases. The one when it's a summation of polynomial number of terms. We saw that this is the case, for instance, in the quantum chemistry problem, and this is also the case whenever we're doing quantum optimization with the QAOA algorithm. But we also said that we would consider cost functions where we're measuring a number of qubits and computing probabilities. So we were then discussing how do we actually extract information from the quantum state so that we can estimate these two types of cost functions. Here we introduced the Hadamard test, the swap operator, and the Hadamard swap test, which a lot of times is just simply called the swap test. You actually saw in Bolin's talk where he was talking about how to actually perform error mitigation. This is something that we're going to be discussing a little bit more in detail tomorrow, what error mitigation is. He was using the swap test because he needed to compute quantities which were like the overlap between two quantum states, quantities of the form the trace of rho sigma, and this is precisely what the swap test does. So I hope that gives you a little bit more of background from what he was doing. We also saw how to compute expectation value of polystrings, of poly operators, by essentially measuring a given number of qubits, computing probabilities, and if needed, performing a change of basis at the end of the circuit. So this is something that we were doing. We also did a little bit of resource analysis of how many measurement shots or what it is that we need to be able to estimate those quantities. After this, we delved deeper into several variational quantum algorithms, specifically the QAOA algorithm, the quantum approximation optimization algorithm used for solving combinatorial optimization problems. We were focusing on the max cut problem of having a graph and trying to partition it to maximize the number of edges between the nodes in the two different partitions. Here we introduced the cost function that is based on the local, the classical version of if the clauses are satisfied or not. Then we also saw how to build the ansatz based on this idea of the adiabatic evolution, and that led us to introduce the quantum alternating operator ansatz, which again shares the same name, but is also QAOA. So then the next thing that we saw was a quantum autoencoder, which is a variational quantum algorithm for data compression. How can we take data in a data set and compress it so that we can encode it into a smaller number of qubits? We saw cost evaluation circuits for this. We saw how to do the encoding, how to do the decoding. We define a cost function where we're measuring a given number of qubits. And we also discussed a little bit about compilation. And you also saw that today Bolin was talking about compilation. Whenever he was saying that he needed to implement those swap operators on multiple qubits, he found different ways to compile them to try to reduce the 2-qubit gates that you were using. So that's a perfect example of how a quantum compilation algorithm can be used, for instance, to try to reduce the depth of a circuit and reduce the noise, the amount of noise that is going to accumulate throughout the circuit, right? In this case, we were mainly focusing on the compilation problem of trying to map one input state and trying to learn the action of a unitary on a given quantum state. I realized that I forgot here to give some references, so let me give you one. This is car T, K, this is a K. Quantum 3, 140, 2019. You can also find this in the archive under the number 1807 00800. All right. And then something that we said is, for the autoencoder and the compilation, we discussed cost functions. We discussed how to evaluate those cost functions using quantum circuits, but we really didn't say what was the structure of the parametrized quantum circuit. What was the ansatz that we're going to use for this U of theta? Whereas whenever we were talking about quantum chemistry, we talked about the unitary coupled cluster ansatz. For QAOA, we talked about the QAOA ansatz, and those two were used for that specific set of problems, because we had some information about the problem that we can take and we can embed into the ansatz to be able to have some idea of what the structure of the circuit could be. In this case, it's not obvious, right? Because imagine that B here, the unitary that we're trying to learn, is completely unknown. What structure should we use for the quantum circuit? It is absolutely not obvious, right? So for today's class, what I want to start us doing is start discussing the problem of quantum ansatz design. Quantum ansatz design. Where again, ansatz just means the assumptions that go into something. So whenever we say what is the quantum ansatz design, so we're just going to be asking what is an ansatz for U of theta. This means what gates are we using? And this has the questions where not only what gates, but where are we placing them? And of course, as you can expect, different structures for the parametrized quantum circuit may have very different performances when trying to solve a given task, right? So it's not obvious what we can do. So here, let me start recalling that we're considering a general form for U of theta that is usually expressed like this. U of theta is going to be a product of E minus I theta j sigma j w j, right? Where j goes from 1 to a given number L of gates. So essentially what this is telling us is that our quantum circuit is going to be a product of unparametrized gates, such as CNAs, and parametrized gates. This, seems extremely obvious, but this is just the general way in which we're going to be writing ansatz. And essentially, both the UCC and the QAOA can be expressed in this form because this is completely general. You just have to be careful about who each W and each sigma and who L is, but up to that, you should be completely fine. So at this point, let me introduce a little bit of terminology. More specifically, let me start introducing, there are two main types of ansatz that people work with. The first is what we call a problem inspired ansatz. Right? Because here, what we do is that we take information about the problem and we encode it and we embed it into the design of our parametrized quantum circuit. So we saw two examples of this. One example is the unitary coupled clustered ansatz, where we saw that our operator or ansatz was of this form, where T was a summation of single body and two body excitations. So why is this problem inspired? First of all, because we're already working with quantum chemistry, and we start with the ground state of with the solution of the mean field equations. Our initial state is the solution is the Hartree-Fock state, and we know that the solution to our problem is just going to be performing excitations over that Hartree-Fock state. This is what Juan Miguel was talking about. So essentially what we know here is that this specific ansatz is creating excitations over the state that is the mini-field solution of our quantum chemistry problem. So this is absolutely problem-inspired. It's made for quantum chemistry, right? We also saw for QAOA that our ansatz was going to be a product of unitaries that look like this, with a mixer Hamiltonian and a problem Hamiltonian. So how is this problem inspired? Well, the problem Hamiltonian is literally embedded into the ansatz. So we are just exponentiating the Hamiltonian that we're trying to get the ground state of to try to, again, loosely follow this idea of the adiabatic evolution. It's not, as we saw yesterday, and as we discussed yesterday from a question from YouTube, it's not an adiabatic evolution by no means. We're completely breaking that, but the idea still remains. In other cases, like whenever we're discussing the quantum compilation or the quantum autoencoder, we don't really have any information about the problem because we might not have anything at all. In a quantum autoencoder, people might be telling us just compress this data set. They're just going to give us a machine that we push a button with a given probability, it gives us a quantum state. We don't know what that quantum state is. We don't know what it does. We don't know its symmetries. We don't know anything about it. So there's no information about the problem to be encoded into the ansatz because there is no information to be had about the problem, right? So in many cases, we're stuck with what are called problem agnostic ansatzes. And here, it's sort of like a worst case scenario where we have no information that we can encode. Into the structure or into the design of our unitary. So what are we going to do here? What's the next best thing that we can do? So usually what people think about here, and perhaps the most famous and the most general in that sense, hardware problem agnostic ansatz, is the very famous hardware efficient ansatz. And this is perhaps what you've seen a lot of times in some of the talks from our speakers. They're showing some circuits, and those are usually hardware efficient ansatzes. So these have two main ideas and two main advantages to them. So the people that propose this, it's in the paper Kandala et al. It's Nature paper 549. Let me make this a proper 549, pages 242 to 246, 2017, and it's also in the archive 1704 0501. So what's the idea of the hardware efficient ansatz? So the hardware efficient ansatz is it's an ansatz made for near term, where the amount of gates that we use and the depth of the circuit is going to be important. So the main idea of this ansatz is that we are going to build a quantum circuit from the gates, from the native gates of a quantum device. What do I mean by this, of a quantum computer? So what do we mean by native set of gates? Usually whenever we have a quantum computer, as we talked quite a bit ago, quantum computers are based in physical systems. So if we have a superconducting set of qubits, or if we have trapped ions in a lattice, usually that means that there are different ways in which the qubits are going to be interacting, right? And the way in which those qubits interact is going to be essentially given by the laws of quantum mechanics and the Hamiltonians of that system or quantum computer is being built. So usually there's a finite set of interactions that is going to give us a finite set of gates that are natural to that device, and usually use those as building blocks to build more complicated circuits. Thus far, we've been assuming, for instance, that the quantum computers that we have can implement any rotations about any of the axes and CNUTs, for instance. So that means that we are going to use those. But of course, whenever we say CNUT, a CNUT is acting on two qubits. It's acting on a control qubit, and it's acting on a target qubit. So how do we know which are the set of native gates? So a lot of times here, what we need to start thinking is about what an actual quantum computer looks like, right? Because whenever we talk about native set of gates, we're not just talking about, so whenever we say native set of gates, let me take this picture and move it further to the right. We talk about those that arise from the native interactions in the device and also by arise from the native connectivity of the device. And this is going to be important because this tells us that we can only implement, for instance, in superconducting qubit connectivity, there is an extra. For instance, whenever we want to implement a CNOT, that means coupling two qubits. And say that we have, these are just different topologies of IBM quantum chips. So for instance, the Yorktown was one of the first ones. It's a 5-qubit quantum computer, and this is how the physical qubits in the chip are arranged and how they're connected. So the lines, here the nodes represent physical qubits, and the lines represents the connections, the physical connections that I can do between those qubits. So for instance, I can make qubit 0 interact with qubit 1. I can make qubit 1 interact with qubit 2, but I cannot make qubit 1 interact with qubit 3 directly. So if we assume, for instance, that IBM can do control X gates, which are CNOTs, I believe that they can do control Z, but let's assume that they're CNOTs. That means that I could do a CNOT between qubit 0 and qubit 1, right? I could do a CNOT between qubit 1 and qubit 2. And those would be native gates in my native gate set, right? So if we're writing a set of gates that is native for the Yorktown quantum device, we would have Z01 and Z12 in this gate set. But of course, we do not have a control node between 1 and 3. In a quantum circuit, this would look like something like this. So we have qubit 1 connected with qubit 2. So this is something that we could do. But if we wanted to do something like this gate right here is not a native gate. We actually can't do this gate. So what we would have to do is we would have to take this gate and we would have to decompose it. And again, we would have to compile it into a native state of gates. And usually this would involve connecting qubit 0, qubit 1 with qubit 2, and then qubit 2 with qubit 3. So you can see that at the end of the day, we're going to build our quantum computer, our quantum circuit with just gates that are actually native, because we already know from here that we can connect qubit 2 with qubit 3. So whenever we're actually writing a quantum circuit, we have to be very much aware of what is the quantum device that we're going to be using, because maybe you're just going to write a circuit that has a given set of CNOTs, but in practice you're not going to be able to implement this. Say that I'm using the Melbourne device. I want to connect qubit 1 with qubit 9. Whenever you draw the quantum circuit, it's very easy to say just put a CNOT there. In practice, I'm going to have to propagate the information between all of the connected qubits to finally make qubit 1 and 9 interact, and this leads to very deep circuits. So the connectivity of the device actually plays a very key and important role. So usually, if you see most of this, at least in superconducting qubits, what we have is that qubits are locally connected. That means that we have a qubit that is connected with its first neighbors. And we can always think about making what we call like qubit chains, right? Where we start with one qubit, and then we just order them in such a way that each qubit maybe is interacting with their first neighbor. For instance, if you wanted to do something like this, and we wanted to use the Melbourne device, and we wanted to make it such that whenever we drew lines, we know that we can always make CNOTs between neighboring qubits, I would just say, okay, let me make this particular assignment. So the topmost qubit is going to be this. The second is going to be this. Then the third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, and then 13. I'm not using qubit 6. That's fine. But what I have now is I have, with this assignment, a sequence of 13 qubits that I know that I can make first neighboring gates. So for the rest of this talk, we are going to assume that the set of native gates which we're going to use to build the hardware efficient ansatz again to reduce the depth and to use only gates that are easy to implement in my quantum device because they are native to it, is composed of. And now we're going to go from the general. We usually said that we have rotations around one of the mu axes. Maybe we have phase gates because we wanted to make a universal set, right? This was the universal gate set that we previously had, but now we're going to make it device oriented. And we're going to say that we still have all the rotations here. Of course, mu is x, y, or z. We're going to have phase gates, but we're only going to have the control x gates. And I'm going to use, let's use CNOT. I don't want to confuse notation. We're going to have a CNOT between I and I plus 1, right? So now we're going to restrict the set of gates that we're going to be using to just having local connectivity so that I can couple my qubits one next to the other. So, of course, the next question is, we've just defined the set of gates. How do we actually build a hardware efficient ansatz? So the main idea of the hardware efficient ansatz is hardware efficient ansatz is reduce the depth and use native gates, as we said. We still have to assume some structure to how we're going to order those gates. And the way in which people usually work with the hardware efficient ansatz is that you're going to have a parametrized quantum circuit that is going to be composed of a sequence of rotations. Oh, that's not going to fit. So I'm just going to say here, like single qubit rotation, because those are part of our native gate set. And then we're going to have a sequence of entangling gates. And what we're going to do is that we're going to repeat this a number of times. Oh, I didn't want to cut it. Can I still paste it? Yes, I can. So we're going to have something that sort of looks like this. And it has this layered structure. So whenever we have a circuit that repeats itself, like the QAOA, we talk about layers. So I'm just going to repeat this, and this is layer 1, layer 2. So the first assumption that goes into the ansatz is already that we are assuming that it has this layer structure. There's something that has notifications on. Let me turn it off. There it is. So we assume a layered structure of single qubits, rotations, and entangling gates. Right. Now we still have the liberty. Who are those single qubit rotations? Who is the entangling set of gates? So the first thing that we can try to answer is, okay, so what rotations am I going to be using here? First, we know that there's single qubits. So this right here, it has no entanglement, right? So we could try to go here and we could try to say, all right, what is going to be now the specific ansatz for just the single qubit rotations? A lot of times, this is, of course, going to be of this form because it's just single qubit rotations. And we can ask ourselves, who is that box that we have right here? In the simplest case, we might just say, okay, this is just one single R mu rotation. And that's all that I'm going to do. I'm going to do one rotation about one of the qubits, and that's that. We can also think about trying to do the more general single qubit rotation, which we know can be decomposed into 3 rotations, for instance, about 3 different axes, RZ, RY, RZ. We know that in 3-dimensional space, just like the block sphere, we can do 3 rotations determined by the Euler angles, and that is enough to determine any rotation that can exist, in the 3-dimensional space. So this right here, if you will, this is the more general. Actually, we've been using blue for tips, so let's try to keep that. So this is here, tip number, let's check it. There's a big tip box right here. It's the one with quantum circuit, so it's going to be easy to find. It's number 7. So tip number 7, this is the more general 1 qubit gate. Of course, it has 3 parameters rather than 1. 1 qubit gate, not parameters, right? So how many parameters would we have if we use this right here? We have 1 parameter per qubit. So each layer of single qubit rotations would give me n parameters. Here we would have 3 n parameters. So we have more expressivity in my circuit, but I also have more parameters to train, right? So that's rather easy to say, to solve. The second question is, who is going to be my set of entangling gates? What are we going to be using here, right? So who is this right here? And here, this is where we have a little bit more liberty and where people usually do 2 approaches. The first is entangle the qubits in a brick-like fashion. So we're going to be entangling alternating pairs of qubits. So here what we're going to have is a circuit where u of theta is going to look like we already said. We first do single qubit rotations, and then we're going to entangle again neighboring qubits, because this is what we assume that we have, like this, right? And we're going to have our single rotation of qubits, and then we're going to encode. Let's say that this is on 4 qubits. Let's just draw it on 4 to keep it simple. That way we don't have to worry too much. I'm going to entangle this right here, this right here. Say that we even have cyclical connectivity, where I can entangle these 2. Then my ansatz would sort of look like this. This is sort of like the ansatz that what Balint was presenting, when he was presenting the ansatz that he used to solve. And this is 1 layer. And again, why are we using this? Because we're just exploiting the properties of local connectivity and single qubit gates. We can also do, this is A, entangle all qubits per layer. So here, of course, what this has is that, I'm just entangling locally. First, I entangle the first qubit and the second, then the second and the third. And it's only after that I do an entangling gate between 2 and 3, right? So here you can see that we put a bunch of parameters in between entangling gates. So if we have another alternative is to use entangle all qubits in a highly, let's just say entangle all qubits. So let me show you the structure, and you're going to see what I mean by this in a second. So here what we would have is something that looks like this. And then I do a highly entangling layer, which would be entangled first and second, then second and third, and third and fourth. And we could even, again, assuming this connectivity, do this right here, right? And then we would do our second layer, alternating single qubit gates, and we would just repeat our entangling gates like that. So this would be 2 layers of my ansatz. So this would fall right here, right? And we just go so forth, so on and so forth. Is one preferred over the other? Well, I would say it depends on the task at hand. This one right here has the property that it is highly entangling. So even 1 layer, even if you cut it here, you're going to be producing states with everyone is entangled with everyone, right? No matter how many qubits I have. But if I have an ansatz that sort of looks like this, and I have a bunch of qubits, and you can think about this like brick-like fashion of qubits entangling one with the other, entangling the first qubit with the very, say with the middle qubit is going to take me a while, right? Because the interaction is traveling locally, right? Each layer, I'm just entangling 1 with 2, then 2 with 3, then 3 with 4. If I have to get to qubit 25, it's going to take me quite a significant number of layers for qubit 25 to eventually see qubit 1. This might be good, this might be bad. It depends on the problem that you're trying to solve. For instance, if you're trying to find the ground state of a Hamiltonian that has local interactions, like the Ising model, usually something like this might be better because we know that qubits in spin chains are entangled with their first neighbors more than they are with their second neighbors and with their third neighbors and so on. Like the entanglement decays as you move away from each qubit. So in that case, maybe this would be a better choice, right? But in principle, it's not obvious what we want to do. And here, let me just say that you can always think about generalization of this. This isn't by no means written in stone. This you can just do what you want, and we can take this idea of if I see this over here, I'll just use this yellowish. You can sort of see that this sort of looks like bricks, right? Where here I have a brick connecting 1, 2, then 2, 3, then I have this brick right here. Then I have this brick right here. And it's just going to repeat itself, right? So a lot of times we call this sort of ansatz like an alternating entangling ansatz. And those bricks, we can generalize them, right? We can just replace them by something that would sort of look like this. So in this case, we just take and we just have like a hardware efficient ansatz. With alternating two-qubit unitaries, right? And why am I saying this? I'm just saying this because now the question arises, so who is this two-qubit gate that we're doing? From a previous example, we know that this is a rotation of one of the qubits, then a CNOT, and then I have something that looks like this. But maybe this is not the more general two-qubit gate, right? We already saw that for single qubit gates, there are multiple ways to do single qubit gate. And we could even ask the question, what is the most general two-qubit gates? And here, I'm just going to give you this reference. And so this is why I'm bringing this up, because I think it's really cool that people have worked on this. It's Vatan Physical Review A 69032315. Year is 2004, or archive 030806 2003. And what they showed is that just like we know that the more general two-qubit gate, one qubit gate is this one right here with 3 parameters, there is actually a way to find the most general two-qubit gate, and it's actually of this one. Let me just write it first, and I'm going to explain what it is afterwards. We have a CNOT here going in this direction. Then we have here a rotation about Z, rotation about Y. Then we have a CNOT going down. Here we have rotation around Y. The CNOT now going up. Yep. And here we have U1, U1. Right, so what is this? We can recognize CNOTs, we can recognize rotations around Z and Y. And here all that we do is that U1 is the general 1 qubit gate that we just saw, that has 3 parameters. So any 2 qubit unitary that exists within the unitary group of the greedy can be generated with this circuit right here. So this is the most general that you can do. It only requires 3 CNOTs, and that's actually pretty cool because that is the minimum amount of CNOTs that you're required to generate any unitary on 2 qubits. You cannot do any unitary with two CNOTs or just 1 CNOT like here. So this is why maybe sometimes we want to generalize it to be more expressible. We're gonna come back to that in a second if that's good or bad. So how many parameters do I have here? I have here 3. I have here 3. I have here 1, 1, 1, 3, 3. So that's 3, 6, 7, 8, 9, 12, 15 parameters. So creating the more general unitary on 2 qubit parameters requires at least 15 parameters. It could be less, but this is the more general case. So this is sort of the idea between the hardware efficient ansatz, that we just exploit the local connectivity to build some arbitrary structure with maybe just local entangling gates or maybe fully entangling layers, and we just hope that we can do the best with this ansatz, right? So you can think about now what would be like in practice the difference between a hardware efficient or between difference between problem inspired and agnostic ansatz. So of course, at the end of the day, what we have is we're trying to do something that looks like this: U of theta rho v dagger of theta O, right? So we're trying to prepare a quantum state that does something. And what we usually have is we're going to be having a set of parameters that we're going to be sending through some parametrized quantum circuit that has a given structure. Maybe it's problem inspired, maybe it's just problem dependent, doesn't really matter. So this is U of theta. And each set of parameters is going to have associated. So let's say that we have here multiple sets of parameters, like theta 1, theta 2, theta k. Each set of parameters, whenever we send it through the circuit, U is a map that maps parameters to unitaries, right? So we're going to have U of theta 1, U of theta 2, U of theta k, right? And then we're going to take those U's, we're going to apply them to our state rho, and we're going to get a collection of states rho of theta 1 in the Hilbert space. So many times what we're interested to see is know if one of those states is going to correspond to the solution of my problem, which in turn means if there is a unitary that maps my original state to the solution of my problem. So let's focus now on the unitaries instead of focusing on the states, right? Usually you can think about the unitary space. So this is the unitary space of degree D. So those are all the unitary matrices of D times D. We usually note this by the set U of D, the unitary group of degree D. I'm just going to add this here, group D, to be completely formal. And this is essentially all the units, or all the unitaries that exist in degree D. Given a problem, what we're going to have is there might be a set of unitaries. Say this is the set of unitaries that solve my problem A. Right? Maybe we have, and what we want to do is we want to try to build a set of unitaries that has some overlap with this right here. So maybe the set of unitaries that my circuit can produce, if it's problem inspired, maybe it's just like this. So this right here is the accessible space by U of theta. If this accessible space overlaps with the solution of my problem, then there will be, I might be able to find a solution by training, right? And a lot of times what we do is whenever we use problem-inspired ansatz, we try to narrow down the space of unitaries that we explored so that hopefully it contains the solution to our problem, right? However, yeah, we have a question from YouTube. Since the hardware-efficient ansatz contains only local interactions, is the ansatz expressivity limited by the Lieb-Robinson bound? How useful is this ansatz for simulating condensed matter systems? That is a great question. So for people that don't know, the Lieb-Robinson bound, it's a bound that determines the speed in which information can be transmitted in quantum systems. So because whenever we use a hardware-efficient ansatz like this, the information transmission in the hardware-efficient ansatz is absolutely determined by bounds such as the Lieb-Robinson bound. And we're also going to have notions sort of like the light cone, how is information propagating, right? So for instance, if I fix all my parameters, but I change the one here, how long is it going to take for other qubits to know that I made this change? Well, first, the information is going to propagate through here. So after one layer, the second qubit, the qubit above realizes, then it's going to propagate through here. And we're going to have this notion of, a sort of light cone is going to start forming in the circuit of how information propagates through it. So yeah, there is absolutely notions of information transmission and information propagation in quantum circuits. And there's people that have looked a little bit into this. But going back to this, right? So this is the problem-inspired ansatz. So this is the accessible space, maybe by a problem-inspired ansatz. And of course, what problem-inspired ansatzes do is that maybe I can solve a problem given an ansatz, like the QAOA ansatz with a given problem Hamiltonian, will solve that. But if I have another task right here, which is maybe UB, now it's the solution for another problem, clearly the problem-inspired ansatz is not going to work for that, right? Whereas on the other hand, the hardware efficient ansatz, it's very agnostic. Maybe the hardware efficient ansatz is just going to be something that looks like this. This is going to be the accessible space by a problem agnostic ansatz. Thus far, you know, you might be starting to think problem agnostic ansatzes don't look that bad, because I can use them for multiple problems. Like this ansatz that you're going to see right here, people use it for absolutely everything. Quantum chemistry, optimization problems, quantum machine learning. It's so agnostic that it can be essentially used for any problem. And thus far, it sounds great. And of course, here we can say that higher volume in the group, this is called high expressivity. Because I've been talking about this, but I wanted to bring it up. Expressivity. And it would seem that having high expressivity in my ansatz is great. I can use it for multiple problems. But as we will see tomorrow, that is usually not the case. Because we know from classical machine learning and classical theory of computation that there are results such as the no free lunch theorem. And what that tells me is that there is no one algorithm that is going to perform well for every single task. And if such a powerful computational results hold for classical computation theory, they probably will also hold in quantum machine learning and quantum algorithms. And actually, they do. They absolutely do. So what we're going to see later and tomorrow is that having high expressivity, while it seems like it's a great idea, it's actually not the best, because it leads to trainability issues, and it can actually be extremely detrimental for you to try to have an ansatz that is as expressible as possible. But we're going to get into those details tomorrow, right? I don't want to spoil myself too much. I've been talking about problem-inspired ansatzes. I've been talking about problem-agnostic ansatzes. There are other, of course, other ideas that you can have. For instance, you can have like variable structure ansatzes, where we've been sort of fixing the structure in both QAOA and UCC and here, and every time that I've drawn a circuit, it's just the same circuit, and we just change the parameters. But maybe we can do something different. So the idea of variable structure ansatz is that now U is going to be a function of two sets of parameters, theta and k. So theta are going to be, for instance, rotation angles, and k are going to be position or type of gates. And whenever we do our optimization here, what we're going to be doing is changing the structure of the ansatz on the fly. We're going to make the optimization a little bit harder, but maybe we can now have a problem that we use a hardware efficient ansatz, but we just don't grow it. We sort of change the structure to sort of like compress this blue area, this green area in parameter space, so that it sort of overlaps with my solution, right? So here the optimization problem is over continuous variables. This is usually continuous variables, whereas gate placements or gate types are usually going to be discrete variables. I'm not going to go into too much detail about this. I just wanted to bring it up that ansatz design is currently one of the most active and important fields for near-term quantum computing, because we don't have a lot of times intuition about what we should be using. If you want to work more and read more in this, this is a paper that we worked with one of our summer students in our quantum computing school, and it's this reference one here. Right. So now I quickly want to mention one more thing. So whenever we're talking about quantum computing, we said that we needed a cost function, and we've already seen how to define cost function, how to estimate them. We said we needed an ansatz for U of theta. We've already discussed quite a bit about that now. Then we said that we needed to take an optimization strategy and an optimizer. Let's now very quickly talk a little bit about the choice of optimizers and how we can actually try to optimize our cost functions. So whenever we talk about quantum optimizers, let me just quickly bring this back here. Optimizer choice. And this is, of course, going to be very relevant for quantum machine learning too. So whenever we're talking about optimizer choice, and you've already started to see a little bit of this whenever we are working with the coding exercises, A lot of times we are just going to be using classical methods that have been developed for solving classical optimization problems. Those can be such as SPSA method, Nelder-Mead methods, Kobila optimization method, Powell. Those are gradient-free because they don't require information about the gradient. And we also have gradient-based, which are optimization methods that use information about the gradient to try to improve our convergence. Those can be like, of course, gradient descent, and all the alternative baits of gradient descent, like, stochastic, gradient descent, Newton, gradient descent, and whatnot. So what are gradient-free methods? Just very briefly, imagine that we have some given landscape that we're trying to optimize over. What gradient-free methods is that they don't have access to the gradient because maybe we cannot compute it, right? So we cannot just compute what's the direction that takes us down the farthest. So for instance, the Nelder-Mead method, what it does here is that it sets a number of points over the landscape given by a simplex, and it's going to compute the cost function at point A, point B, and point C. And then it's going to determine which one of those points has the smallest cost function value, and then it's going to transform the simplex to start moving in that direction. So it's going to be moving the simplex around, comparing different points in the landscape, trying to see which is the direction that takes it down the best, right? Gradient descent is, of course, based on the fact that if we're standing in a landscape, what we can do is we can just compute the gradient of the cost function, which is just the vector obtained from the partial derivatives of my I'm going to call it object function because this is classical, and it's going to tell us the direction of steepest descent, right? So the question is, how do those methods perform in quantum computing whenever we're trying to train our quantum computing or quantum machine learning model, because they're essentially the same. So this is what people started doing whenever near-term quantum computing and hybrid methods started to arise. They were just using classical methods. And we realized that, they work well, but maybe they don't work as well as expected. And the first question that you should be asking is, well, gradient-based methods, we need to have access to the gradient. Can we actually access the gradient in a quantum computer? And this is one of the theoretical exercises in the theoretical guides, but I want to still mention it, which is computing gradients on a quantum computer. Because, of course, it's not obvious that given a function, I'm always going to be able to estimate the gradient, right? I might always be able to do some sort of finite difference to approximate the gradient, but that doesn't mean that I'm actually getting the proper gradient. It's just an approximation. So the question is, can we actually get the true gradients? And surprisingly, for quantum computing, the result is that yes, we can actually access the exact gradients on a quantum computer, which is pretty cool. So I'm going to give you two extremely important references. Unitary PRA 98 03 2309 2018. This is on the archive 1803 00745, and Schuld PRA 99 03233 2019. This is on archive 18111184. And what those two papers show is that we can exactly compute the gradients in our cost function. So let's recall what are the assumptions that we've been making to sort of understand how this is derived. So the first thing is that we know that our cost function is going to be of this one. So we have rho u dagger of theta O. And we've assumed that u of theta is some general circuit that has a form that looks like this: e of minus I theta j divided by 2 sigma j w j, where sigma j is just some polystring. It's just some poly operator, like local rotations, right? This is what we've been saying. So the next question is, all right, based on those two assumptions, how do we compute the gradient? How do we actually do this? So we need to compute something that looks like, for instance, the partial derivative of the cost function with respect to the kth parameter. How do we go about doing this? Right, so I'm just going to give you a few tips of how to derive this result. I'm not going to do it because it's one of the exercises. So the first tip that you should know is that taking the partial derivative of x of the trace of a x is equal to the trace of partial derivative of x of ax. So we can take the trace and put it inside partial derivative and put it inside of the trace. So that already tells us that if we take the partial derivative of c, we can take this and put it inside. So that means that we can take this and we can just express this as the trace of the partial derivative of theta k of u theta rho v dagger theta o. The next thing that we should do is, okay, we're going to take the partial derivative of a function of a matrix multiplication, right? And here we have multiple things. So you have u rho, and u dagger also depends on theta, right? So we have two functions that depend on theta here. So the second thing that you need to do is the partial derivative of x of ax b cx, and then it's going to be, is we just apply the product rule. That's nothing but what we have to do. C of x, and here we're going to have, let me draw this properly, a of x b the partial derivative of c of x, right? So we know how to take this partial derivative and distribute it here. Then we need to know how does the partial derivative of u of theta works, right? And you're going to be able to compute this. And at the end of the day, once you run through all the math, and there's some tips that you're going to have to use. So I recommend definitely checking all the different tips that are on the theoretical guide. What you can show is that the partial derivative of my cost function with respect to a parameter theta k is going to be expressed in this very simple and beautiful formula. C of theta plus minus C sorry, of theta minus, where theta plus minus is defined as my usual vector, theta 1, theta 2, and when I get to theta k, I do plus minus pi over 2. Then I keep going to theta L. So what does this mean? Let's just take a second and look at this equation. This equation right here is called the parameter shift rule. And it is extremely important because it gives us a way to compute exactly the partial derivative of a cost function with respect to a parameter by just evaluating the quantum circuit with a different set of parameters. So imagine that I had something that looks like this. U of theta perform measurements, right? So this is how we estimate the cost function. Okay, so the parameter shift rule is telling us, okay, take the circuit, don't change the structure. The structure remains the same. All that you have to do is change one parameter in one gate. So let's call it theta plus k, because it's in the kth gate that we're doing this, right? And use the same circuit evaluation, use everything that you've already developed to estimate your cost function. You're going to use it to measure it by just changing that one parameter with plus pi over 2. We do the same to estimate that parameter with minus theta over 2. I think I'm switching the notation here. Yes, I am. Plus k minus k. Use your same framework, and you're going to be able to estimate these two quantities right here. Then just subtract them, and that's it. You have your gradient. So this is extremely powerful and extremely cool because not all the time you have access to the gradients analytically. Of course, this comes at a price. This comes at the cost that how much does it take us to estimate the full gradient of my cost function, right? So this is a vector that has the partial derivative of theta with respect to theta 1, and so forth, right? So it's the vector of the partial derivatives. Okay, we know that if we use the parameter shift rule, we have to, for each parameter, I have to estimate this cost function. And say that I have here n shots. Here I have n shots. So the cost of each gradient could be 2 n shots. And if I have L parameters, this has a cost that is 2 times L times n shots, because we have 2 n shots per parameter and we have L parameter. So the total number of shots to estimate the whole gradient is 2ln. It scales linearly with the number of parameters. So the more parameters I have, the more shots I have to put in. So, you know, this is something that might be considered like weakness of this method, because it's extremely expensive shot-wise and time-wise to compute the gradients, because we have to do this at each iteration step, right? So it could get very expensive. At the other time, let me then just very quickly say that this parameter shift rule has other very important and powerful implications. For instance, we can try to check what is the absolute value of this partial derivative, right? How large can it be? Because we know that if I have a landscape that sort of looks like this, it's very smooth. My gradients are not changing that much, right? Because the gradient is how steep this function is. But if I have something like that looks like this, like sort of very close to a discontinuity or very rough and broken edges, this means that I can have extremely large gradients, right? And I can just drop all of a sudden. Well, we know that this from the parameter shift rule is just the expectation value of c theta k plus, alternating this again, plus k, c theta minus k, right? And we can just use the chain. Let me just take this. I'm going to make it smaller and put it here because we're going to require more space. We can use here the triangular inequality for the absolute value and get something that looks like absolute value of c plus k plus c theta minus k. And then if we know that the cost function is bounded, for instance, if we know that the cost function is between 0 and a given maximum value, then we know that each one of those cost function values is going to be smaller or equal than C max, which is just the maximum number that the cost function value can reach. A lot of times this is finite. This is just like 1, because we normalize our cost function so that it's between 0 and 1. So in this case, this is smaller than just C max. And this means that we cannot have broken edges, because if our cost function is normalized between 0 and 1, then we know that this is at most 1. So that means that our gradients, at no point I can have something that has a steepness that is larger than 1. I cannot have extremely broken or extremely big drops. So you can already start to see how we can start to understand the quantum landscape through properties that arise from, you know, the linear algebra nature of quantum circuits, right? So this is pretty cool that we can start understanding properties of the quantum circuit, right? So this tells us that the landscape of VQAs is not rugged. And a lot of classical machine learning landscapes are very rugged. They can have like big broken edges. This is not something that can happen in variational quantum algorithms. So we have a question from YouTube. Could you please comment on the computational cost of calculating the gradient with respect to the number of parameters? I believe this is what we did here. So essentially, it scales linearly with the number of parameters. But of course, here, you know, something that we need to take into account is that we are putting here n shots, right, to estimate each component of the gradients. And something that classical methods don't take into account is that quantum computing is probabilistic, and we need to perform measurements to be able to extract information from the quantum computer. So a lot of times those optimizers are going to fail because they don't take into account the fact that, again, quantum computing is probabilistic, and those are methods that have been developed for classical computing, and they will underperform in quantum computing. So there's a whole other field, which again, I'm not going to get into, but I want to mention it, of quantum aware optimizers, which are optimizers that are specifically designed to optimize variational algorithms and quantum machine learning models. So I can give you here 2 references that you can go check, and from there you're going to discover a whole new world. 24.06.5252. So this should be 252, and we have Cool Bear 124.263 2020, or the same paper you can find it on archive 1909-1903. And those papers, for instance, what they're trying to do is, do we really need to use n shots to estimate the gradient? Or if I have an operator O, as we've said, that is expressed as the summation of a bunch of polystrings, do I have to estimate the expectation value of all of them to be able to estimate the expectation value of O? And what people have done is trying to reduce the computational cost of doing the optimization. For instance, whenever you have something like this, it's been shown that you can just randomly pick some of those sigmas at each iteration step and sample which one I should be estimating to estimate O. And how many shots do I need to do once I pick those sigmas to estimate the sigmas? A lot of times, even just one single shot in my quantum computer is enough for me to get an unbiased estimator that I can use for training, right? So this is just to say there's a lot of work that is being done in developing quantum-aware optimizers. All right, and I think this is exactly where I wanted to get, because now I really want to start talking about properly quantum machine learning. It took us a while, but you're going to see that all the tools that we've used is everything that you need for quantum machine learning. Quantum machine learning is essentially near-term quantum computing with an extra added thing. So everything that we've seen thus far is going to be useful here. Are there any questions up to this point? Before we delve into the world of quantum machine learning proper. Okay, so let's just start talking about quantum machine learning. So what's the idea of quantum machine learning? So the idea is we want to use quantum computers to learn from data. We've already shown this sort of image in the first class, but I want to repeat it. So you can think about a VQA as being a problem where I have an input, I write a program that is defining my cost function, the ansatz, and whatnot, and I'm going to get an output, which is the solution to the problem. In QML, we sort of invert this, and we think about, we have an input, and we have data that we already know, for instance, a label, so we have an output. And what we want to get is the program, right? And quantum machine learning has been essentially envisioned for all the tasks for which machine learning can be useful, right? So we know that machine learning is an extremely broad area, and there's many things that you can do. There are things like supervised learning, right? Let me just move this here. There's also unsupervised learning. Here we have tasks such as clustering, right? Here we have tasks such as regression or classification. And quantum machine learning, as we said, has been envisioned for all of those tasks. So we can think about QML, and it's going to be exactly the same. We can do QML for supervised learning tasks, for regression, or for classification. Similarly, we can do QML for unsupervised learning tasks, such as clustering. In the remaining of this lecture, I will try to just focus on one particular implementation, and that's going to be a quantum machine learning supervised classification task. So this is going to be our focus. But essentially, QML can be used essentially for everything. So the question here is, what is it? What is the setting? What is the framework that we're going to be working on, right? So let me just first define a few couple of terms that are going to be useful for us. So we're going to be talking about, let me just give you the complete framework, right? Specifically, we're going to be talking about classification. So that means that we're going to have a set of data that has a set of labels, and what we're trying to do is learn what is the map between that data and those labels. A classical machine learning task for classification with classical data is, for instance, having pictures of dogs and cats, training a model that is going to tell me this is a picture of a dog, this is a picture of a cat, right? So here the data is pictures, and the label is someone already went through the work, and there is a bunch of photos that we know that they are dogs or cats, right? And we want to train the model that does the classification. So here we're going to have a very similar framework. So let me start with defining the framework of work. Framework for supervised classification. Because we can't really talk about a problem without defining the mathematical framework where we're going to be working in, right? So we are going to the notes, and this is, if you've had a machine learning course, this is going to be how every machine learning course about, or the theory of machine learning course starts. So this is just going to be a nice refresher. We define by X the set of all possible examples or instances. And usually we also call this X as the input space, right? And then we denote by Y the set of labels or target values, right? And for our case, because we're doing classification, we're just going to restrict ourselves, and we limit ourselves to the case where Y is just the set of -1 and 1. So it has only two labels. They are discrete. -1 can be dog, 1 can be cat, right? And this is what we usually refer to as binary classification. Right? And of course, the whole thing about machine learning is that we assume that somehow there is an unknown map. Unknown is key here, that maps between instances and labels. And this is, of course, what we want to learn. Right? So what we're going to do is that then the next thing that we're going to have to assume is that we have a way to draw examples independently and identically distributed. This is what people usually call as IID, right? So we can draw examples according to some. This can again also potentially be unknown distribution D. This means that we can actually access data. We can access data and we can access the labels, right? So now with this framework, we can define the learning problem. And this is at the key of machine learning. So what we have is that we are going to draw IID according to that probability distribution D. a bunch of examples that we're going to use. Those examples, we're going to divide them into a training set, which we're going to call S, and a test set, which we're going to call T. And here what we want is, given a possible set of maps, right, or what we call a hypothesis set, right, we want to train a quantum machine learning model, which we're going to call as H tilde and belongs to the set M over the training data so that the predictions of H tilde, which is our model, match those of H, which is the true model, with high probability in. So where do we want them to match? We want them to match with high probability in the training set. This is what we usually call low training error. But we also want on the test set, which is composed, of course, of previously unseen cases. So these are not models, not cases that we use for training our model. And this is what we usually refer to as low generalization error. So a key aspect of the training in quantum machine learning is that whenever we're working with variational quantum algorithms, we just wanted to get low training error because that was our output, right? In quantum machine learning, the problem is more complex, and we don't just want low training error because already our model was trained with photos that someone already labeled, right? So that's not exactly what we want to use it for. That's not as useful. What we want to do is we want to train our model so that it performs well on previously unseen cases, so that now we have this way of doing the classification for us without us having to label it beforehand, right? And it's actually quite easy to create an algorithm for machine learning that has zero training error, but generalizes very poorly. For instance, you can imagine that we hard code, so, why low training and then just correct training error does not mean low generalization. Well, for instance, you can think about a trivial case where we have a model that memorizes all the training data set. So that means that xi, whenever I feed it a data that was in the data set, in the training set, it's just going to give me the correct label. And if I feed it label that is not in the training set, so xi is not in the training set, then I just give label -1 and 1 50% of the time and 50% of the time. So it randomly guesses what the label is. Of course, this has zero error over my training set, right? It's completely memorized. But whenever I feed it unseen data, then it's just going to be random. It's just flipping a coin and telling me what's the label for that data set, right? So essentially, this is a way in which we can see that in quantum machine learning, what we care for is about the generalization error that we get, not just about the training error. And this is just, of course, an extreme case, but it's just for you to keep in mind that you have to be a little bit careful, right? So let's start thinking a little bit more specific about why do we want to use quantum machine learning and why do we think that there could be some quantum advantage coming here. So let me just put this image right here because this is going to set our basic framework for quantum machine learning. And I want to spend a little bit of time looking at this, right? So now we have the mathematical framework. How do we actually get that model, and how do we actually do the training? I want a little bit further. There it is. So what does the QML model looks like? So quantum machine learning, just like in general variational quantum algorithm, first it can be envisioned to work with classical data and quantum data. We saw that there's VQAs to solve classical problems, and there's VQA to solve quantum problem. Well, it's similarly, it's the same idea for quantum machine learning, right? So we can have quantum data, like the one that you have to prepare for the hands-on exercises, which is going to be literally this. You're going to get collections of states that belong to some different phase of matter and are the ground states of some Hamiltonian, right? How do we build a classification problem? Well, if we have two phases, we just sample states from, say, maybe a ferromagnetic phase where states are aligned, and from a paramagnetic phase, right? And we know their labels. This could be all the states that are in this phase is labeled +1. All the states that are in this phase is labeled -1. And that's the data that I'm going to be working with, right? How do we deal then with classical data, right? Classical data is not obvious because my classical data it's not in a quantum computer, right? So the first thing that we need to do is think about how to take classical data and put it into a quantum computer, because the quantum machine learning model, essentially what it's trying to do is trying to do some process analysis over quantum states. And that means that the first thing that we need to do is a way for that classical data to be put into the quantum computer, because as we said, the first thing about quantum machine learning is that the main goal here is to use a quantum computer to give our hypothesis H access to the exponentially large Hilbert space, right? So whenever we have quantum data already lives in a Hilbert space. So then I can just think about how do I process that information, and we're going to get that in a second. But for classical data, what we need is that, say that we're trying to classify pictures of dogs and cats. I first need to take that classical data and I need to put it into a quantum computer. And this usually requires what we call a data embedding scheme. So for classical data, and this is going to be the first thing that we're going to be focusing ourselves, is for classical data, we need to map the inputs onto quantum states. Oh, that's not going to fit here. Onto quantum states, right? So we have to have a way to take, for instance, a real valued vector and put it inside of a quantum state. This should be rho that depends on this vector xi, right? And I think that this is the first thing that we're going to start studying. We're going to start analyzing different ways in which we can do this. And the general gist of quantum machine learning is already expressed in this picture. We're going to get into more detail about this in a second, but I just want to finish by mentioning, once we have our data, be it classical or quantum, in the form of quantum states, the way in which a machine learning model works is that we're going to take that data, we're going to send it through a quantum neural network. That's what QNN stands here. And we're going to take the outputs of this quantum neural network, we're going to perform measurements to compute some expectation values. Those expectation values are going to be used to build a loss function. Note that I'm using here the term loss function, so I'm going to start making a differentiation of cost function is used for VQA, where we have no training data, and I'm going to use loss function for QML whenever we have classical data. Whenever we have data. So QML has data, then it's a loss function. VQA does not have data, then it's a cost function. And then once we have this loss function, we're gonna try to optimize it. And usually this means using a classical optimizer to get a new set of parameters that we're gonna throw into our QNN. So if you just look at the right-hand side of this
Marco.
picture, yeah.
Sorry, I apologize for the interruption. Yeah, but I have a question. This is a simple question, but I have a query. This is okay. So you have classical data, and you are going to represent the classical data using quantum data, or how is the business? Because I don't understand how you transform the classical data in a quantum system. That is a part that I cannot imagine.
That is going to be precisely what we're going to be seeing after the break. The first thing that we're going to be seeing is how to take classical data and put it into quantum states. How do we embed it? There's multiple ways, and that's literally the first thing that we're trying to do, because that's the first natural question that arises. So that is a great question, and I think that we can answer it probably after our coffee break. So if you can hold those for 30 minutes.
Okay, sorry, I apologize. Okay.
That's a great question. It's the first natural question. So I'm just going to hold it off for 15 more minutes. So essentially what I wanted to say is that if you look at the right-hand side of this picture, this is essentially the same framework that we have for when we were doing variational quantum algorithms. And this is why all of the tools and all of the framework that we previously had, like, and I bet you can get this. You can guess this. What is a quantum neural network? It's a parametrized quantum circuit. What do we do here? Compute expectation value of some operators. So everything that we've done thus far is going to be useful, and it's going to translate from variational algorithms to quantum machine learning. So that being said, I think that we can take our 15-minute break. So it's 10:56 for me, 11:56 for those in Guatemala. So I will see everyone in 14 minutes. So that means that I will see you here at 12:10. Yes, 12:10 your time, 11:10 my time. So yeah, I'll see everyone in just a bit, and we'll tackle the question of how to get classical data into quantum states. Okay, welcome back, everyone. So in this second part of the lecture, we're going to be talking a little bit more about the different ingredients that go into this picture. So just like we did with variational quantum algorithms, and we're gonna take a quick trip down memory lane to try to go back to the picture for variational quantum algorithms. We were sort of discussing everything that goes into here: how to define the cost function, how to define an ansatz, how to estimate cost function, measurement outcomes, what does the output look like. So we're going to try to do something extremely similar for quantum machine learning, so that by the end of this lecture, or hopefully by the end of tomorrow's first part of the lecture, you're going to be able to look at this picture and sort of understand at least the basic ingredients that go into doing into solving a learning task with a quantum computer. So as we said, and let me re-emphasize this, the main goal of quantum machine learning is that we want to give the learning model or hypothesis access to the exponentially large Hilbert space. So that means that once we're working with classical data, and as we said just 15 minutes ago, what we want to do is we want to take that classical data and somehow put it into the Hilbert space, so that we can do information processing tasks on the data in this higher dimensional space. So let us first consider the case whenever we're working with classical data. That's the top part of this picture. And here, what we're going to assume is we're going to assume that the data set is of the form xi, yi, where these again are the labels. And this right here, they can be, for instance, bit strings, or they can be real valued vectors, because we know that ultimately classical information can be represented in the form of bits and bit strings. So we can always try to boil down whatever representation we have on our data into something of this form, right? So as we said here, the first step is to embed the classical data points x, I, onto quantum states that my quantum machine learning model can work with, so that a quantum computer can use for information processing. So here, there is not one single way or one single recipe that we can follow to embed classical data into quantum data. There's actually multiple ways in which we can do this, and let us review some of them. So the first type of way is called the basis encoding. And this is particularly useful whenever we have real numbers and we want to perform arithmetic operations. So here, the main idea is we are going to take either a bit string or convert real valued number into bit string representation, right? So here x belongs to 0, 1. Tensor, let's assume that we have a bit string of dimension m. So the goal here is that we promote the classical bit string into a quantum bit string. So for instance, if m is equal to, we have n qubits in our quantum computer, then this is pretty simple, right? For instance, we can take, if we have a 3-bit state, and we want to convert this into a quantum state, then we simply prepare this state that we can use for quantum information processing. How do we even do this? This is pretty simple. We have a quantum circuit where we know that we can initialize everything on 0, and we know that we need to bit flip the second. We can do this with an X, right? So here we know that we get 0, 1, 0, and the tensor product is precisely the state that we wanted to get. So here we can take, and the whole data set can be expressed in a superposition So we have state for the data set that is going to be 1 over the size of the data set, summation over I, going from 1 to the size of the data set of our states xi. Of course, if we have, if m is different than the number of qubits, we can always pad it with zeros if we want, or just use less qubits, right? So this method has some advantages. So it's easy to implement, but it also has some disadvantages. For instance, it is extremely wasteful because we're taking assigning to every bit 1 qubit, and we already know that 1 qubit can contain more information than just 1 single bit. In addition, we have the probably largest problem that quantum mechanics is linear. We take a quantum state, we can implement unitaries to it, and applying a unitary just gives me a linear combination of the elements of the vector that it was applied to. So we can only do linear operations, and a lot of times in quantum machine learning, performing non-linear operations in the data is what leads us to getting something interesting and trying to learn from that data, right? So, basis encoding was one of the first things that was proposed, is definitely something not that is widely used at all. Then we also have something perhaps a little bit more used, which is called amplitude encoding. So here, the data is embedded into the amplitudes of a quantum state. So here, what we do is that we take x, which is going to be a real valued vector, like x1, x2, xm, and what we do is that we express this into a quantum state. So we're going to take this data and just put it into the amplitudes, the coefficients of a quantum state psi, right? So this actually has allows us to write, for instance, here, the state of our data sets can be expressed as 1 over the size of s, summation over I, going from 1 to, sorry, this is the state associated with qubit 1. Sorry, let me just go back here. Let me first do 1 qubit, 1 state of x. Here is going to be something that goes summation j going from 1 to m of xj divided by the summation of I of j going from 1 to m xj squared. This is to normalize it because quantum states need to be normalized. And then I have a bit string zj. So the elements of my vector now became the probability amplitudes in some computation, in some basis. In this case, we just pick the computational basis, right? Where here zj are just elements of the computational basis. This should be 0 and 1 to the n, right? And of course, then we can just build a quantum state for data set. Just the summation with, I should use I now, going from 1 to the size of the data set of those states x i's, right? So this has also some advantages. So the first advantage is that it is widely used in many quantum machine learning algorithms, especially quantum machine learning algorithms that were first developed for fault-tolerant quantum computers. Those use this amplitude encoding algorithm. Then it's also very qubit efficient. Why? Because if we have a bit string of length m, then we just require log 2 m qubits to encode a bit string of length m. Right? Is it obvious why we need this many qubits? Well, we know that if I have a number of qubits which is equal to log 2 m, what's the dimension of the Hilbert space? Then we know that it's 2 to the n, which is equal to the log 2 m. So this is a Hilbert space that is of dimension m, which is precisely how many elements we need to encode into a quantum state. So this is very qubit efficient. And that also means that if our algorithm is polynomial in the number of qubits, it's going to be logarithmic in the size of the data. So this is the main idea of why people thought that you could use this encoding for getting a quantum speedup, right? Because it's exponentially, it's the runtime, an algorithm with a runtime that is O poly n, then it becomes O poly log m. So it's polynomial. It's a logarithmic, it's a polynomial of logarithms and the size of m, which is usually what we want for trying to get a quantum speedup, right? Of course, just like everything good, it also has some disadvantages. The first is that it is not obvious how to prepare x, right? How do we get a quantum state that is of this form? It's not easy. A lot of times we have to fine-tune or even optimize, fine-tune or optimize circuits that prepare those states. Right? And of course, in many cases, this is also linear. Or it can be linear if you're not careful about it. So, we don't want to do this. This is mainly thought for quantum machine learning in the fault-tolerant era. The next one that we're going to be discussing is the one that people most widely use in near-term quantum computing, which is, where did this come from? Wait, what? Oh, it's a figure. Oh, there it is. No, we're red. So it's the quantum circuit encoding. So here, what we're going to do is we are going to use the values of x as parameters in an embedding. I'm just using embedding and encoding interchangeably, right? Circuit. We go back to this idea of parametrized quantum circuit, which we really like as models for near-term quantum computing. So the main idea here, and let me just give you some references for this because there's quite a lot of work that has been done on this. So we have Lloyd. Let me split this into two because it seems like a U. Lloyd, archive, 2001 03622. So this is 2020. We also have Hubrechtsen archive 2105 02276 2021. Then we have Someone archive 2105 02276, and this is of course 2001. And we also have Research Nature 567 209 212 2019. You can find this paper on the archive 1804 11326. So what is the main idea here? And by the way, you can start seeing how some of those papers, this should be 2021, are extremely recent, right? A lot of papers from this year right here. So this is, again, a very active field of research. How to get classical data into quantum states, it's something that we're still trying to understand. So what's the main idea here? The main idea is that we initialize qubits for fiduciary, easy to prepare states, such as the all zero states, right? And then what we're going to do is that we are going to send them through a quantum circuit, which I'm going to denote as E for embedding or encoding, that depends in the parameters of X. So this is a parametrized quantum circuit. And here there's two things that you can do. Those structures can have a variable. Let's start with the first one. They can have a fixed structure or a variable structure. So you can also try to train a good embedding scheme, right? That's something that people have worked on. Just like in parameterized quantum circuits, you train what's the structure of the ansatz. People have thought about training the embedding scheme. So if you want, let's try to be a little bit even more specific and think about what is, how does this actually look like, right? What is an ansatz for this embedding? So in this paper right here, the last one, people propose to use an embedding, E of X, that is composed of a sequence of layers where each one of the layers is going to be, let me just write one layer, J is smaller than K, E of minus I, X, I, J, X, I. So this is the ith K, Z, J, Z, K, product of J equals from 1 to n of E of minus I, X, I, J, Z, J. So here I'm using the notation that the vector X, I has components X, I, 1, X, I, 2, and so forth, right? So these right here, the parameters in the rotations are given by the elements of this real valued vector, right? So how does this look? Let's just paste it. Sort of looks like this. This is an example for 3 qubits, right? You can see that what do we do first? We do a rotation in every single qubit where the parameter is determined by the entry, the ith entry on the qubit, right? So the ith rotation on the ith qubit is determined by the ith entry of the X vector. So in this case, what we're doing, we're using a scheme where the length of the vector is equals to m and is equal to n. But then this is just linear, right? We are also doing some nonlinear operations, where what we have here is that then we perform this e to the some parameter. We already know how to implement this. Remember this quantum circuit, we've already seen this. So you should recognize this right here, because we've already seen this, as just entangle the I with the jth qubit and perform a rotation that is determined by the ith component of x and the jth component of x, right? So here, just as always, this has some things that we like about it. For instance, this is easy to obtain non-linearities. And this can also be interpreted as a quantum kernel. What we don't like about this is that it's not obvious, yet again, what ansatz to use for E of x. In principle, there could be many that we could implement. So here, just by just quick question for people that are taking the class. Do you know what a kernel is? Do you have some experience in machine learning? Would you like me to explain this? Do people here know what a kernel is so that I can explain a quantum kernel? A shy bunch. Have you heard kernel before? Okay, I see that people say, no, I don't know what this is. Okay, let me try to explain. So now we're just going to go into a detour of some concepts of classical machine learning. So let's talk about the kernel. Oh, that's not a T. The kernel trick in machine learning. So the kernel trick is, imagine that we have data that is not linearly separable in some original input data space. Because a lot of times in machine learning, what we want to try to do, so I see here in comments, is it when you have feedback from the environment? Not exactly. So here what we have is, imagine, let me try to give a more specific example, right? Imagine that we have data that are just real values. And a lot of times what we want to do in in classical machine learning is that we want to try to separate data, because again, we're thinking about binary classification by just putting some hyperplane through it, right? We just want to, if we have data that lives in a two-dimensional space, we want to draw a line that splits the data. But a lot of times we cannot just do this, right? For instance, you can think about data that are real values. And here we have the origin. And my data is split as such. We have some data that belongs to one class that sort of looks like this. And then I have data that belongs to another class that sort of looks like this. So now here you can see that I have a problem if I want to try to do just a linear decision boundary, right? I can't just say, oh, I'm going to draw a line here. Everything to the left is one class. Everything to the right is one class. This is not something that we can do. So the idea of the kernel trick is that we apply a transformation to the data, right? And map it. Sorry, just give me 1 second. Excuse me. Okay, sorry, I am back. We apply a transformation to the data and map it to a higher dimensional space. Where we try to fit a hyperplane as a decision boundary. So here, for instance, we can see that if this is my data, x1, something that we can do is we just embed it into a higher dimensional space, and now my vectors are going to be x1 squared, right? So how would this data look here? So now we would have something, oh, I should have done it like this, where my red data is going to be of the form 1. Right? I'm just taking my data, squaring it up, and that's what we get. And now here, you can see that there is actually a way to feed a plane that is going to split my data so that everything that is on top of this plane belongs to one class, and everything that is below this plane belongs to another class, right? And this is a trick that we can do not just from 1 to 2-dimensional space. Imagine now that I have a 2-dimensional space where I have data x1, x2, and this data is in this form. Oh, I should have done circles here, shouldn't I? Yep, so we have colors. Right? There is no plane that I can draw through here that allows me to do the linear classification. Something that I can do is I can take this vector x1, x2, and then I can just apply some linear map to it. So let me just call this the linear map to x1 was this, x1, x2, that maps me into a 3-dimensional space that is going to be this form. Right? Now, what we get in this space is something where the data is going to be like here. Those should have been x's. Let me just be consistent. You can try to remake those plots in a prettier fashion if you use Python or Mathematica, and double check that what I'm doing is correct. And here, of course, I can draw a plane that is going to separate the data, right? So here I can have a linear hyperdecision boundary. So the kernel trick, again, is used to analyze data in the higher dimensional space. But a lot of times, this higher dimensional space, it could be pretty large, right? We could be trying to take data and maybe it's not enough just to go to one dimension higher. Maybe we have to go to a much higher dimension. And then we've got ourselves a problem because now we have to try to deal with data in that higher dimensional space. So a lot of times what people in quantum machine learning do is instead of actually mapping that data into higher dimensional space and performing operation in that higher dimensional space to try to see if you can actually solve the problem, people what do is that they just care about computing the inner products of data in that higher dimensional space. Why the inner products? Because the inner products is a distant measure, and it's going to tell me if my data in that higher dimensional space are the points closer together on one class and farther apart from the points in the other class. So the kernel trick is taking the vectors from the original space right? And return the inner product in the higher dimensional space. And that's all the information. It's been shown that that's all the information we need to try to find the decision boundary, right? And of course, this is usually denoted as if we have data x1, data x2, and the map phi. What we can do is build this kernel, usually denoted like this, x2, which is just the inner product between phi of x1 and phi of x2. Why is this enough? Because the main idea is that in this higher dimensional plane, we still need to solve an optimization problem, right? We still need to find where that line is. So I see that there's a question in YouTube that says, from Chris Harry, that says, is there a relation to image processing kernels? Yes, everything that has kernel in its name is this idea of trying to embed your data into a higher dimensional feature space where you're going to do the information processing. So I'm guessing I'm by no means an expert in classical machine learning, but as far as I've read, everything that has kernel in its name is going to be related to this basic idea. So as we were saying, right? So once we map to this higher dimensional space, we still have the task and the goal of finding the decision boundary, right? And this essentially means, imagine that we had data that looks like this, x2, x1. Let's be consistent. Red was x's. We have here circles. So what we need to do is we need to find the plane that sort of separates the data, right? And that plane is going to have some minimal distance to points. Let's try to add one more here so that it's not that symmetric, that belong to each class. And you're trying to fit a plane that is sort of like the farthest apart from the closest points from each class. And this is a method. I'm not going to go into the details of this because this is not a classical machine learning course, but this is essentially what people call support vector machines, or SVMs. And here, the idea is that we solve the optimization problem, right, of determining the hyperplane that separates the data by class. Right? And here, what's important is that data points with minimum distance to the hyperplane are called the support vectors. And these are the ones that are playing the most important role because due to their closeness to the boundary, their influence on the exact position of hyperplane is larger, right? And what people do here is that this optimization problem of trying to find what the decision is. Where the boundary is, it can be solved and can be solved via I'm not sure why I'm writing in gray, via the kernel KXI xj, because again the kernel is just making a statement about the distance between points, and here we're trying to make to feed a hyperplane that is that sort of like it's the farthest away from the closest point, so that it separates the data to the best of its ability. So if you get the kernel, you can try to use a support vector machine to find this. Again, the main idea is here not to go into the details, right? So why do we then say, and this was quite a big detour, but we said that this is easy. This has the pro of that we can interpret this as a quantum kernel. So how can we interpret this embedding that we have as a quantum kernel? Because again, we're taking classical data, X, and we have a map, phi, which in our case, what it does is that it gives me states in a higher dimensional space, rho of X, which are obtained as applying E of X to some easy to prepare state, for instance, such as this, E dagger of X. So we already have this idea of taking classical data and putting it into a higher dimensional space. So the idea of quantum machine learning for classical data that we just sort of assume that maybe it's a good idea, it's already based on the fact that this is what people do in classical machine learning to solve machine learning tasks. You take classical data and you put it into a higher dimensional space where maybe the data is separated. Well, that higher dimensional space, which we usually call the feature space, it just happens to be the Hilbert space, right? And that's why we sort of have the intuition that maybe quantum machine learning for classical data might work because it fits in the framework of quantum kernels, right? So here, what we want to try to do then is you can think, what's the kernel here? That's the kernel. So we just compute k xi xj. That's just the trace rho xi rho xj, and then we do a support vector machine for classification. We fit this hyperplane, right? So this is the first way in which we can think about quantum machine learning, where we simply use this higher dimensional space to embed my information and then try to do my classification. And that's perfect, right? We can do this, but as you might be wondering, this sort of doesn't fit this framework. Like, we haven't even talked about quantum neural networks right here. And this is something that happens also in classical machine learning. In classical machine learning, whenever we want to do classification, we can do kernel methods with support vector machines, or we can use neural networks. And we can do the same with quantum mechanics. We can sort of try to generalize this idea of kernels and support vector machines to just use your Hilbert space as a way to encode your information into a higher dimensional space and try to classify it there. But of course, again, the kernel method, we know that it has some nice property, but it also has some disadvantages. It could be that the kernel might not properly bifurcate the space, or maybe a hyperplane, and just trying to do the classification by fitting a plane is not enough, right? So what do we do here? We go to the next thing, which are in machine learning neural networks and in quantum machine learning. Let me go back here and just close this up. Quantum neural networks, where the main idea is that now we are going to try to do the classification by first doing some operations on the data in this higher dimensional space. Because classically, whenever we're working with classical kernels, the whole idea of the kernel trick is that we don't have to do operations into this higher dimensional space. We're just computing their inner products and then fitting a plane. We're never dealing with data in this higher dimensional space. Well, you know what? In quantum mechanics, we sort of can, because we can prepare the states in a quantum computer, but we can also easily act on them, right? So why not just, instead of just trying to feed a plane, also try to do a quantum neural network? So of course, as we will discuss later, you can always still think about this as a kernel method. But for now, let's just focus about a model where we take classical data, we send it through some embedding scheme, and we're going to get now rho of xi, right, yi. And if we have quantum data that already belong to different spaces, to different phases, we have something that looks like this. And even if my data was quantum or classical, at this point, it doesn't matter. At this point, I'm just going to assume that I have a data set composed of states that live in my Hilbert space and labels. So from this point onward, I'm not going to worry too much about, is the data classical, is the data quantum? I don't care. I just have quantum states with labels associated to them, right? So yeah, I'm going to leave that. That's fine. So once we have those quantum states, we want to perform information processing tasks on them, right? And that's the thing that we want to do. Oh, just before, very quickly, I forget, because I actually forgot. I think I mentioned it, but I'm not sure. Oh yeah, easy to obtain nonlinearities. Yeah, I wanted to bring this up again. This data encoding already gives us nonlinear operations from the elements of our original vector, right? So what's a quantum neural network? And let me just paste this figure here again, because we're going to be using it. I'm just going to make it smaller. Right. So we have data, and now what this picture says is we send our data and we send it through a quantum neural network. So let's say the first thing that we need to know is that I'm going to denote this as QNN. And what they do is that they generalize classical neural networks for information processing. Based on the laws of quantum mechanics, right? In practice, what we're going to get is that we have a set of quantum states, xi, with labels iy, and it said this can be quantum data or encoded classical data. I'm just gonna not care too much about this for now, and these are going to be, of course, labels. And what we do is that we're going to take each one of those quantum states and we're going to send them, as we said here, through this quantum neural network. And at the end, we might perform measurements on some or all the qubits. So what is a quantum neural network for the purposes of this course? And to no one's surprise, QNN is parametrized quantum circuit. So now you can start to see how parametrized quantum circuits have been playing a key role since we started this course, right? Why is it that we keep coming back to parametrized quantum circuits? Because if you remember, based on what we were originally discussing, what we can do with quantum systems is that we can apply voltages, pulses, fields to individual constituents of quantum systems, right? This is the way that we interact with quantum systems and with qubits. And those translates into unitary operations. So that's the way that we control them. So that's why at the end of the day, it all boils down to, I am just going to build a sequence of those pulses or a sequence of those gates that is trying to do some information processing tasks that I want. So this is precisely why parametrized quantum circuits are going to be playing a key role for variational quantum algorithms. for quantum machine learning, for the quantum neural network, for the encoding scheme, because they are at the core of what we can do based on the laws of quantum mechanics. And of course, it's just like saying, any classical algorithm at the end of the day is based on the same set of rules. It's just that we're using those rules for different purposes and with different structures to achieve different outcomes. This is essentially the same. And in the near term, parameterized quantum circuits are the way in which we think about processing information in a quantum computer, right? So now the next question is, and let's follow this picture, we're gonna perform a series of measurements. And what we can say is that here, so take a quantum state. Oh, this is not working properly. There it is. A quantum state rho I from the data set. Right? Send it through, I think there might be an extra H here. I never remember. Let's just get rid of through because I don't remember how to spell it. Send it in the quantum neural network, i.e. parameterized quantum circuit. And compute some expectation value via measurements. That's starting to sound really familiar, right? Because this is what we said that we can do in quantum computers. Prepare states, send them through circuit, measure, and compute expectation values from there. So usually what we do is that we're going to define via measurement. So we're going to define some quantity Li of theta. And now I have a label that is just going to be send my quantum state, send it through the quantum neural network. From here onwards, I'm going to start using U of theta for the parameterized quantum circuit of the quantum neural network, right? Apply the source state rho I and measure some operator that maybe depends on the label associated with that given state, right? Then we're going to take those measurement outcomes and we are going to compute the loss function. And the loss function, now I'm going to denote it as L of theta. I'm no longer going to be using C. It's going to be a summation with I. It goes from 1 to the size of the data set of a given function f of those quantities Li, theta, Yi. And this can also be a function of the true labels Yi, right? So this right here that we've presented, this is the framework for using quantum neural networks for quantum machine learning tasks. The who is O right here is defined by the problem at hand. Who is F right here is defined by the problem at hand. So again, this is a completely general framework. And you can see that at the end of the day, we use the quantum computer for the thing that we do, just set a quantum state, evolve it, and measure. But this is not telling you too much, and I'm pretty much aware of this. So let's consider one specific example that is going to illustrate how to do quantum machine learning. So consider an example, and hopefully this is going to help you to clarify things. So imagine that now we want to do a problem of binary classification on quantum data. So that means that X is just subspace of the Hilbert space. It's just a set of space that belong to a given subspace. Y is going to be -1, 1. And those are the two sets that we defined as the input set of the input space and the label space from the learning framework, right? That we discussed just a bit ago. So the first thing that we need to discuss and we need to come up with is how do we take a quantum state and we assign a label to it? We need to do something, but at the end of the day, we want to assign label -1 or 1. We want to say, is this a cat or is this a dog? Is this ferromagnetic or is this paramagnetic? So we need to come up with a way of assigning labels, right? One way that we can do it is we can assign labels via measuring k qubits, where obviously k is smaller or equal to n. So we could measure all of them, we could measure some of them, and estimate the number of bit strings so this is via measurements. We already said via measurements, so I don't want to be redundant. The number of bit strings with even, odd, parity. If I measure, I get a bunch of bit strings, I check their probabilities, I add all the bit strings that have even probability, even parity, odd parity, and if I have more bit strings that are even, I will give this label 1, and I will give this label -1. So let me give you an example, right? To be a little bit more, ground this a little bit more. Imagine that I have a 2-qubit state that encodes information rho I. I send it through a 2-qubit quantum neural network, and at the end, I'm just going to measure. I'm going to measure both of the qubits, right? Let's say that I decide to measure both of them. What are the measurement outcomes that I can have? Is 0, 0. Those, and I'm going to have a number of times that I got 0, 0. Can get outcome 0, 1, 1, 0, and 1, 1, right? And those with the respective associated number of times that I got measurement outcome. We can also divide by n and have the probability of 0, 0, probability of 0, 1, probability of 1, 0, probability of 1, 1, right? And this is just the frequencies. Now, we said that what we're going to do is we're going to count which is more probable, if the bit string has even parity or odd parity. So the first thing that you might be asking yourself is, how do we compute the parity of a bit string? So let's just be technical and define parity of Z is the number of ones in Z, and we do this modulus 2. So this has parity even, because there's no ones. This is odd, this is even, and this is odd. So in this case, all that we have to do is we say how many outcomes had even parity. Well, that's just going to be n 0, 0 plus n 1, 0. We can ask the same question, how many outcomes had odd parity, and that's just going to be n. Wait, I'm doing something, sorry, this should have been like this. I messed it up because those two are odd. And this is also even because it has 2, and 2 is an even number. So I just realized this now as I was writing it here. Excuse me about that small mistake, but this is n 1, 1, 1, 0 plus n 0, 1. And essentially now we just assign the label depending on which one had the most, right? Which one had the largest number of bit strings at the outcome. And that's the way that we're going to do this. Is this the only way in which we can assign a label 1 or -1? Absolutely not. This is completely arbitrary. This is one way to do it, right? And you can come up with other ways. And each different way that you define how you're going to extract information from your quantum state could lead to some potential advantages or issues, right? This is still not within this framework. What we're going to say is that let's try to write this into this form right here. So, for instance, using the previous framework, we can now say the probability of assigning label yi, which I'm going to denote as p of yi given theta, is going to be the trace of u of theta rho I u of theta. And I'm going to measure again here one operator oyi that depends on the label. What is oyi? So I know that O1 is the summation onto the projector onto Z being even, right? And O minus 1 is the summation onto the projectors OZ being odd, right? Why is this true? Because we know that whenever we put the summation inside of this expectation value, I'm going to get a summation of probabilities. And this is essentially what I'm doing. I am adding up what is the probability of getting all the measurements that I have even parity, or the probability of all the measurements that have odd parity, right? So we can actually think about this as P00 plus P11. They contain the exact same information plus P01, right? So those are the measurement operators that we're going to be using for our classification task, right? And we're talking about what is the probability of assigning a given label. Now, maybe you don't feel comfortable about talking about using probabilities of labels. Maybe you feel more comfortable if the measurement outcome is in itself a label, right? We can also try to come up with that. So in this case, we can also think about a framework instead of the measurement outcome being a probability. Let me get rid of this. The measurement outcome can be a label by itself, can be in itself the assigned label. So for instance, how do we do this? Now let me define a quantity which is the assigned label y theta, which is going to be the trace of, I take my state, and now I need to obtain a number. I was missing a dagger here and here. That is between -1 and 1, right? Because my label, my true label is a discrete value that lives between -1 and 1. But for now, what we can do is we can assign a number that is somewhere in between there. And I'm going to try to get it as close as the true value, right? So something that we can do is we just have to measure some operator which has an expectation value that lives between -1 and 1. And we can do the same by where instead, before we were measuring k qubits, we said, and we were projecting into bit strings, now we just measure the expectation value of z to the k. Why? Because this is a number that lives between -1 and 1. And of course, be very mindful that this is a continuous label. This is not a discrete label like the true labels, right? We're going to see in a second how do we actually still recover the discrete labels, because I don't want a function that is going to tell me, oh, you know, this is closer to cat than closer to dog. I want to have, at the end of the day, a discrete value. But for the purpose of training, it's completely okay for me to have a label that is continuous rather than discrete. So now this is a number that the closer it is to, for instance, if this is a number that is very close to -1, that means that the quantum neural network is sort of recognizing, or the model is sort of recognizing this data as being closer to the label -1. So we have a question from chat in YouTube that says, what if the label is not binary? Yeah, that is absolutely a great question. So something that we've been doing thus far, as we said, is we're just considering binary probabilities, right? But in principle, we could do it differently. So let me just very quickly, in square box right here, imagine that you're trying to do multi-class classification. And now you have, say, 4 classes, right? Why 4? Because it's easy to map to binary. So I'm going to have class 1 is going to be, I'm going to assign it to a bit 0, 1. Then I'm going to have 1, 0, and 1, 1. So these are going to be my labels, right? What I can do now is I can measure 2 qubits, and let me think about probabilities like we were doing. What is the probability of me assigning a label? So what I can do is I measure 2 qubits. I have my quantum system, and I'm just going to pick 2 qubits that I'm going to measure. I'm not going to do anything to the other 2 qubits, and I'm going to check what's the probability of getting outcome 0, 0, probability of outcome 0, 1, probability of outcome 1, 0, and the probability of outcome 1, 1. And I'm going to assign the label in this class, in this case, to whichever has the largest probability. So if P00 was larger than the other probabilities, then I assign this as my true label. So there are ways in which you can deal with multi-class classification whenever it's not just binary. It's just that for now we're considering binary because it's the simplest case, and I just want to get like the framework done. So I hope that answers the question. So going back to the original problem, and by the way, are there any other questions up to this point for people that are here? Okay, fantastic. So as we said, we have 2 ways now. We have one way, which was trying to get a probability of assigning a label given our set of parameters, and we have the measurement outcome being a label in itself. Now, of course, what's really cool about quantum mechanics is that we can use linear algebra, and we can prove that these 2 approaches, like approach number 1 and approach number 2, so approach 1 and 2 are equivalent. So assigning a label or assigning a probability of a label are exactly the same. Why is this? Because you can prove that z to the k is just equal to a summation with z even z minus summation with z odd z, which means that z to the k is equals to O1 minus O minus 1, right? And now we just we use this fact and we can prove that the assigned label is essentially going to be given by the probability that I get 1 given theta minus the probability that I get minus 1 given theta. And concomitantly, we can say what's the probability of assigning a label y. And this is going to be, this should not be like this. This is 1 plus y I. This is the assigned label divided by 2. So, of course, now we've been working with continuous variables, either the probability of a label or the label in itself. But at the end of the day, for the purpose of accuracy testing, so that's whenever I ask my quantum neural network, I give it a picture, and I say, is it a dog or is it a cat? Is it ferromagnetic or is it paramagnetic? For the purpose of accuracy testing, we need a discrete value. So here what we can do is we can have a rule that says assign label yi if the probability of yi given theta is larger than the probability of minus yi given theta. And as simple as that, we were able to map a quantum state center of quantum circuit. We perform measurements and we get just a discrete value, where now this is going to be called y hat I, is the predicted label, and it belongs to the set or label. So the next thing that we want to discuss here is, so if we go back here, now we know how to extract information through measurements out of my quantum state. We can give meaning to those quantities L that we were previously discussing, right? So now we know what those L can be interpreted as. They can be probabilities of labels, they can be labels in themselves. We still need to define the loss function. So what are loss functions that we can use for quantum machine learning? So a lot of times we can use the same loss functions that are defined for classical machine learning, although recently there's been more study in developing loss functions that are specifically meant to be used for quantum machine learning. But in the meantime, some of the most common loss functions, and then just put this like this, common loss functions are, for instance, let me do it like this, mean squared error loss function, which is defined as MSE for mean squared error, which is going to be I sum over each point in my data set. And what I'm going to be checking is how far is the assigned label from the actual label. So of course, you can think about this as I'm trying to minimize the distance between the assigned label and the true label for each data point. This is going to be 0 or close to 0 if this number, that again, it's continuous, it lives between -1 and 1. So this is not, again, remember, this belongs to -1 and 1. How close it is to the true label, right? We can also use the negative log likelihood loss function. And this is defined as L log is equal to -1 over the size of the data set. As usual, I'm going to sum over all the points in my training set, and I'm going to be taking the log of the probability of assigning label I. That seems too much like a G. And this is what we're going to get, right? So here our loss function, and you can see sorry about that. So what we have here is that our loss function is made as a summation of the log of probabilities. So you can see the probability of me assigning the correct label. So now this right here is the correct label. If the probability of assigning the correct label is very close to 1, the log of 1 is going to be very close to 0, and we're going to be very, very close to solving the problem, right? So essentially, these two are probably the most common loss functions, and using this framework right here, we get both probabilities and both assigned labels. So you could potentially use any of those two loss functions for training your quantum machine learning model. So I think this is, with this, we can wrap up the specific example of binary classification where we've seen how to run through all of those steps and try to give you like a general idea of how everything works, right? Those are like the general steps that you should follow in your recipe. So are there any questions at this point? Okay. So I do want to go back and just very quickly mention something because we're very, very close to ending our class. I think this could be a good stopping point. The next class, we're going to look at now what is the structure of this QNN. Now we've just been saying send your state through a QNN, but we haven't said what the QNN is. So next class, we're going to be studying some structures for QNNs, what are ancestors for QNNs, and what we can expect from them. But I just wanted to go
Marco,
back. Yeah.
I apologize. Yeah, could you scroll down to the last part in the likelihood probability equation, please? Oh, okay. So that's okay. The question is why the log?
So the log is because what you want to do is that you want to try to penalize probabilities that are small.
Okay, and the other question is I have seen that in some analyses they use the likelihood test that is approximate that is a division of likelihoods, but the question is, okay, here we are supposing that our state space is defined so that we don't need an extra element, right?
What do you mean by extra element?
Because I'm a bit confused because, for example, I understand that you have to apply a log likelihood test when you are not sure if your model completely fits your data. So you apply the likelihood test in order to have a point where to say, okay, this is working or this is not working. Let's move to another model with an extra element. But the question is, in this case, we have to do the likelihood test, or we have to stay in this way?
You could potentially do it, right? Because the framework of the tools that you have for classical machine learning in principle can be implemented here too. So you could run your likelihood test to check if your model if you need to add something to your model. In this case, it could be, for instance, add another layer to your quantum neural network, or add more expressivity to your quantum neural network. So those tools that you have for classical machine learning, you could always use them again in quantum machine learning. You just have to reinterpret like what the features of your model are, right? What the hyperparameters of your model are that usually fine tune via running all of those tests. You just have to translate and understand what's what, but in principle, you could try to use all of that framework.
Okay, yeah. So, the question is because recently I was working with the Fermi Pi tools. That is like, yeah, you download the data from the Fermi satellite, and at some point you have to do the likelihood test in order to use an extra source of radiation in your region of interest. So that was just a question related to this. Okay, so I appreciate your answer.
Right? No, thanks. That was a great question. So the last thing that I want to mention, and I'm just going to go back a little bit, is I want to talk about embeddings and just say something important whenever we're talking about embeddings, which is what do we want from an embedder, right? What are the different properties that an embedder should have? So the first thing that we want from it, and for some reason, it is working. This is not working. Just give me 1 second. My pen stopped working. Sorry, let me try to troubleshoot this. I think it might be running out of battery. I think I have another one here. But let me just explain this, and I can go back to this tomorrow. So what we want from the embedding scheme is, first, we want it to be classically hard to simulate, right? Because think about the kernel methods. If we can efficiently compute the inner product of states that are the output of the embedding scheme, then why would we want to do that kernel in a quantum computer, right? We can just do it classically, and there's no point in running it in a quantum computer. So the first thing that we want out of a kernel is for it to be classically hard to simulate. The second thing that we're going to want out of our quantum kernel is for it to be practically useful. Because if we've seen from those examples that we had whenever we were talking about the kernel, we want it so that in our higher dimensional space, our data is well separated. And it could be potentially that whenever we run, whenever we send our data to this new feature space, the data is not well separated. So that means that our kernel is not practically useful. So our kernel should, in principle, be the inner product of states at its output should be classically hard to simulate, and it should be practically useful. And I gave you one specific example of a kernel, which was the picture that we had right here. So this is a kernel that in the paper that I told you that it was coming from, this one in the bottom right, the Nature paper, they show that it's based on a circuit whose outputs are classically hard to simulate. So this is an embedding scheme that is believed to be classically hard to simulate. So, you know, it checks one of the marks, right? It's a classically hard to simulate embedding. So the next question that we can ask is, well, is it practically useful? Can we try to do something practical and useful with it? Well, this is a numerical experiment that we ran using this embedding right here. So this is what we call the classically hard embedding. So this is CHE in the plot on the right. And here you can see the value of the loss function in the y-axis versus the number of iterations. And on the left and on the right, you have the test accuracy. How many of the points that we're sending through it is being accurately classifying. And what we did here is that we took classical data, specifically we took classical data from the MNIST data set. So we took handwritten digits of 0, 1s, we embedded them using this circuit, and then we also compared it to a hardware efficient embedding, which is this HEE that says here with only one layer. And the HEE embedder, it's not classically simulable, right? It doesn't have a lot of entanglement. It sort of has the structure of the alternating pairs of qubits. So imagine that it exactly looks like this one right here, right? So we use this to embed our classical data where the rotation angles were given by the parameters of our classical vector. So that's classically hard to simulate. It doesn't fulfill one of the two conditions of the embedding. So the hardware efficient, not classically simulable, the one that is shown right here is not classically simulable. Is it good? Well, whenever we're trying to train, you can see by the red curve, and we train multiple models. That's why the curve have a little bit of a band around them. That's the statistical deviation from the mean, which is the dashed red curve. You know, whenever we train it, the loss function doesn't go that much down. And whenever we try to see how well it generalizes, whenever it's trying to classify handwritten digits of 0 and 1, we get a test accuracy of about 65%, which is not great. Whereas the other embedding, the scheme, which was, it's completely classically simulable, it's hardware efficient, so it's not based on anything. We just used it because why not? That one is good to train, and we can get classification accuracy of above 90%. So this is just to say that the choice of embedding scheme is difficult. There is by no means one that I can point to and say you should use this embedding, because we still don't know what's a good embedding scheme for classical data. And tomorrow, whenever we're going to be discussing about the difficulties for variational algorithm and quantum machine learning, just like we were discussing what's the choice of ansatz for a parametrized quantum circuit, the choice of embedding is going to be very important. And it's still, again, and I've been repeating this for quite a while, an active area of research where we still need a lot more work to try to find good embedding schemes that are going to be classically hard to simulate and are going to take us to a Hilbert space where the data is well separated, right? So with this, I think that we're in a good stopping point. I just want to give you a preview of what we're going to be discussing tomorrow in our final class. The first thing that we're going to be doing is discussing different structures of quantum neural networks. So I think that one of the questions that we had for our first lecture on the first day was, do we have generalization of classical neural networks, right? So do we have like convolutional quantum neural networks, feed-forward neural networks? How do we take those elements that were developed for classical machine learning and put them into the quantum setting, right? So we're going to be looking at some of the quantum neural networks that have been developed. That's going to be the first half of the class. And then the second half of the class, we've been talking about NIST devices. We've been talking about noise, but thus far there hasn't been noise everywhere. We're going to be talking about the difficulties and the challenges that we expect for machine learning, for quantum machine learning, and for variational quantum algorithms, such as, are the parameters are going to be actually trainable? Are all the choices of ansatz the same? Are all the choices of cost functions the same? Here we have the freedom of selecting who OI is. Is the choice of O going to be the same for everyone? And we're going to be talking, I promised this for today, but we're going to look at it tomorrow, about parent plateaus, which prevent me from training parameters in a parametrized quantum circuit, from noise, and from where the challenges and, you know, again, the exciting thing is for quantum machine learning. So with that, I thank everyone for your attention. I hope that it was a great class. Are there any questions that you have before we wrap this up? Okay, thank you very much. So have a great rest of your day, everyone, and I will see you all tomorrow. And for people that are here, I will see you later in an hour for our hands-on class.